if the class was paramount, why are there only 1, 2, 3, 4, 5, 6, 7, 8 people in this paramount class today? Explain to me why. Because they're going to come in later. That's what they're going to do.
No, because maybe
It's cold.
It's not cold. It's not cold.
Rain.
No. So I don't know. Obviously the problem is that the continuity in this class is for shit. I don't know if I can believe that. Anyway.
Well, it doesn't have to be good.
No. So
It just has to be interesting.
it just has to be interesting.
Maybe if the lecture has more continuity, the class would be too.
The lectures have continuity. I've been talking. Look, I was talking about the cosmic distance ladder. I'm still talking about the cosmic distance ladder. What more continuity could you want?
Topic.
What?
A different topic.
A different. This is a good topic. I use this topic to essentially talk about the whole universe. What else would you like me to talk about?
You know what I like.
I know what you like. You like multiverses.
Right.
You want me to talk about multiverses. Okay. They're at the end of the cosmic distance ladder. Okay. So we have to climb the rungs of the cosmic distance ladder before we can get to the multiverse. We listen. There's nothing I can say about the multiverse, right? I mean, except for good idea, unprovable. What can you say? I covered the multiverse. You want me to cover it in more words? To introduce more uncertainty into this equation?
No, because they have reason to believe that it exists. So explain the steps.
No, I get it, but there's no way that we can get beyond it. I was reading one of the last things that Stephen Hawking did before he died was he wrote a book along with another guy because he doesn't type that fast, and it was about I forget, but it was a speculative tour of the universe and the multiverse.
So talk about that.
Right, but how many times can I talk about the multiverse? Because it's
Well, I give you all these topics that I
right.
I want to know.
Anyway, you don't know about this topic. What do you know about the large-scale structure of the universe? Seriously, what do you know? I'm talking about the whole universe, and you want something bigger.
No, I find it very hard to conceptualize the size no matter what you tell.
Right.
So it's not. That's not. You know.
So multiverse is something you can conceive of.
Yes.
Not one universe, but multi-universes you can conceive of. But one universe, too small for you to get your head around. So multiverses, that's your thing. Okay.
Among others.
Among other things, yes.
String theory.
Huh?
String theory with 11 dimensions.
Right. I love that.
You love string theory?
Yeah.
So we'll start on the early algebra, then we'll work up to the middle maths,
You
and
lost
then
me at early out.
and then we'll do the entire because the thing about string theory is that it's all in the math, every bit of it, and the reason it's in the math is because the math is so beautiful that it gives the people who are working in it such fantastic pleasure. But there's absolutely no evidence that anything they write is true,
But
and they know that.
how much evidence do we know about any other theory?
Okay, thank you. That was a good question. Okay. Now look, what you see here, okay? What you see here on this screen, okay, is the universe, the large-scale structure of the universe. So there is, but what exactly? How big is this thing on the screen? Well, it says 125 megaparsecs. And the word parsec, we got to get used to the fact that they use the word parsec and sometimes light year. And all you got to do is just think, a parsec is 3 light years. Why do they do this to me? So just when you hear the word parsec, change it to light year, multiply by 3, and you'll be happy. Okay, but I'm not going to necessarily make that change back and forth. We will talk about. You don't know what a light year is?
I mean, I know.
It's very big,
Yes.
bigger than this room,
Bigger than a bread box.
bigger than a bread box. Right, but of course you don't know what a light year is. All right. Look, how's this? The Voyager spacecraft that they have out there, there was a problem with one of the instruments. Because see, they're running out of power, and two of the instruments turned on at the same time, and that's a no-no because there's not enough power for both of them on at the same time. So the spacecraft went into a mode which said fail-safe, and it just said, I'm shutting down, let me know what I should do. So the people back on Earth got the signal, and they said, okay, we will send a signal back to you to explain what you should do. Okay? And they did that. We sent this spacecraft out there beyond Pluto. Okay? And we sent the signal to the spacecraft beyond Pluto. And it took us 37 hours before we got a reply. That's 2 light days. You want to know what a light year is? Multiply by 365. That's a light year, or 150 or whatever. A light year is how long it takes light to get from here to where it is that you want it to get to, or from there where you thought it came from to here. 4 years from the nearest star.
So how many light years is it to the end of the universe?
That is a question which has an answer. At least if you phrase it differently. How many light years is it to the end of the universe? Okay. There, of course, you do know that we don't have an end to the universe, per se. We always insert observable universe, so we can get away with, talking about it. Because at the end of the universe, it could be infinite, in which case you might as well go home now. Because
So
if it is,
telling me it's so important that I know how big it is.
well, because there could be, because you want multi-universes. You want multiple universes. And I don't know exactly how I'm going to give it to you so if it's infinite. So I'm just going to say the observable universe, then right next, so the observable universe is a marbled universe, which has an end, which by the way is not good science. And then next to it, there's another multi-universe. See, we talked about multi-universes. There you go. Okay. So each of one of these multi-universes, if they all existed at popped up at the same time or whatever. So ours is, let's say, a typical multi-universe, and it is 90 billion light years in diameter. Does that work out for you? Anything? Does that help you? Of course not. Because what does that mean? It's another number, right? All right. So you can't. So I refrain from trying to do that, trying to say those numbers, although of course they say them all the time. The point is to what I can do to get your attention, and this is something I can use to get your attention. This is 125 million, not billion, million light years, or parsecs, so multiply by 3, okay? So is this a picture of the universe? Is this like, oh, wait, hey, the universe looks like that? No, actually. This is some dream concocted by a computer program to invent the universe inside of its brain. And then when it has invented the universe in its brain, it spits this out and it says, the universe looks like this more or less.
Well, what is all that stuff?
This stuff is dark matter. Because the universe, as you know, is made up of 100%, 75% dark energy. What's that? I don't know. It's dark. I don't know. But it's certainly not matter. It's energy, so it's not things. It's just things between things. The things between things is the dark energy. Then you have the dark matter, which is another, I don't know what that is, because we don't. Okay? And then what's left over is us, which is matter. So 5% of the 100% is matter, 20% is dark matter, and 75% is dark energy. We'll leave the dark energy out because that would just simply confuse things at this point. So now we got dark matter and we got matter. This is only dark matter. dark matter.
What's the little golden form there?
Okay.
Two of them.
So if every galaxy is a dot, okay, and because this has been concocted, these are not dots per se. They have length and width, but they are essentially small enough for them to be dots. So on the screen you see lots of dots, and if you put a lot of dots together, the dot becomes bigger. And if you put a lot more dots together, the dot becomes brighter as well as bigger. So the brighter something is, the more dots there are in that spot. Okay? But it's still dark matter. This is a dark matter map of a small portion of the universe. And when I say small, I mean teeny. Like hardly any part of the universe at all. We, on the other hand, in this picture would be one of these little dots. If we were in this picture, which we're not, because this isn't a picture of us in our nearby neighborhood, this is just a picture of the computer's simulation of us, then we're just one of those little dots. And all of these dots, these millions of dots that we see here, are nothing compared to the trillions of dots that make up our universe, trillions of galaxies. So we're in this picture.
You haven't said what the little golden is. That
So the little
multiplicity of little dots.
The golden thing in the middle of the picture is a multiplicity of little dots. It means we call that a supercluster. We call this clusters of galaxies. That is a supercluster of galaxies. A supercluster of galaxy is, we are part of a supercluster of galaxies. We belong to the Virgo supercluster of galaxies, of which consists of 1,000 galaxies directly in the cluster and maybe thousands more outside of the center of the cluster. So I have that somewhere. Okay, so this is the Milky Way, and you can see, as I zoom in on it, you can see that it's about 100,000 light years in diameter. The halo of our Milky Way, meaning we live inside of a bubble of dark matter, and that extends maybe 1 million light years in each direction. So this is more like 1 million light years. You can see so that's 100,000 light years from one end to the other. And as we go out further, hold on. Yes.
Why is it shimmering?
Why is it shimmering?
It seems to be shimmering.
If it is shimmering, the reason it's shimmering is because I am running 2 pieces of software at the same time. One of the pieces of software is taking pictures of the screen. So this screen is being recorded by the computer at the same time it's showing you this. There's a lot of computations being done in order to get this on the screen. So, this is our Milky Way. You can see it receding into the distance. And I'm looking now for the Virgo cluster. And if I can't find it very quickly, what I'm going to do is I'm going to ask the software to zoom in on it. Okay, so I'm asked the software to zoom in on the Virgo cluster. There it is. And now I'll set this thing in motion so you can see again. So there's the Virgo cluster. We just passed it. Oops, come back.
Virgo West?
I actually told it to go into Virgo West, which
And
is
an east and north and a south?
apparently.
Huh. Are they more expensive?
Yes, more expensive. The Virgo cluster is much more expensive in the western regions. Right, exactly.
Where the rich people.
That's where the rich people are.
Mountains, yeah.
Okay, so I am now at the distance of about 100 million light years, and this picture is also at the size maybe of 500 million light years. So let's look again. This is our actual neighborhood, and that was a complete computer simulation of a region in our neighborhood similar in size. And you can see that there are bunches of things, clusters, and there are bunches of things, and that is superclusters. And what we're seeing here is real data, whereas what we're seeing here is imaginary data. What they did here, in order to get this to happen, is they said, aha, I know from other stuff that I have learned that the universe is made up of dark matter, dark energy, regular matter, and what I'm going to do is I'm going to take those three things and I'm going to put them in a pot according to the level of ingredients, the 20%, the 5%, the 75%. I'm going to put them into a pot. I'm going to create 1 billion particles, and I'm going to subject those billion particles to those laws of physics. Run the supercomputer for 1 billion years and see what we get. And when you run the supercomputer for 1 billion years, you get that. What I'm going to do is I'm going to play some of these simulations for you. And you get that, which matches very well the way the universe actually looks, because I'm going to show you more pictures of the universe. So when you see pictures of the universe, you're going to be confused as to whether or not I'm showing you a simulation or the actual universe. Does the universe have these filaments? Does it have these voids? Does it have these central points where things seem to cluster? And exactly in what proportion? Because look, there are big voids and there are big clusters. So is that the way the universe is? And the answer is yes, that is the way the universe is. And it gets that way only after you let it cook and steam for 13.5 billion years. Otherwise, it doesn't look like this. The universe.
What does it look like?
What?
What does it look like?
What does it look like?
We don't know.
No, we actually do know, because we have pictures of the universe. See, if you look out far away into the sky, the further you look, the younger the things are that you're looking at, and the more babyish they become. So if you are an infant universe, and you are yet to form this intricate web of stuff, then what you look like is not big galaxies. What you see is little galaxies. Let me show you that.
Is the universe going to die?
Is the universe going? Well, no, no. Unless, of course, something else happens. You can ask 100 astrophysicists, and you will get one that will say yes. But that guy is crazier than the others. He's also very well educated. So he has an idea. Okay.
What is it?
His idea is that because you want the universe to die, because that's why you asked the question.
Well, if it ages, then.
No, if it ages, it can get infinitely old.
It's born.
It can get infinitely old. There's no reason why you can't do that. So you want the universe to die, and there are many ways of having it die, but the best one is to have it simply disappear. Okay? How about that? So the universe is, you like strings theory? This is one universe, this is another universe. They're separate from another. Notice I'm not drawing them like this, I'm drawing them like this, okay? And because they're like this, these are called branes. This is one brain, we live in one brain. There's another brain, people live in that brain, okay? And then the brains are always separated, but at one point they touch, and when they touch, the universe explodes and you start a whole new one, okay?
So that's maybe what happened in the Big Bang.
Right. So I give you a dying universe for your pleasure, okay? But otherwise, most of the universes that you invent just go on forever. Okay. Every universe that everybody invents has an infinite lifetime. There's no reason not to.
So the guy who says it's going to die, what's his theory?
M theory. It's called string theory. So he's not an idiot. He's got 4 PhDs. So he has a good idea. It's just that he can't convince the other PhDs that his idea is better than their ideas. Okay? Yes.
But isn't there a nursery of baby
Yes.
items so that nobody has to die? They're constantly being born again.
Right. So that's the multiverse business. Okay? You want the multiverse. Then you have constantly being formed universes.
Yeah.
Right. That's the multiverse. In the multiverse, which is all that Elaine ever wants me to talk about, there are constant rebirths or births, not necessarily rebirths. So try to imagine this: the universe is infinite, and it has an infinite amount of energy. And every now and then the infinite amount of energy over here decides to blow up and expand, okay? So it's not a singularity that it comes out of. It just says, I'm far too bored with where I am, what I am doing. I think I'll simply expand and inflate and create a new universe. So, and that will be this multiverse over here. So multiverses can pop up all the time. That's without discussing inflation, which needs to be discussed in order to have that conversation. This is a possibility. Okay, but try to stay in our universe. Okay, I mean, let's keep our eye on the this universe. So in this universe, we can take a picture of this universe, and the picture here is of a. This is a picture of our universe. It is taken through a soda straw. The soda straw is 2.5 miles long. The telescope focuses through the soda straw. So all of the universe that it can see is the amount of universe it can see through a 2.5 mile soda straw. And this is what it can see. In this picture, there's a piece that's chopped out here. In this picture, you can see 10,000 galaxies. You can see 10,000 galaxies. And not a single star is in this picture, because what they did is they pointed the soda straw, the telescope, in the direction where the sky was absolutely black. And there were no stars whatsoever. And then they left the telescope pointing in that direction for a couple of weeks to take what could be a nonsensical picture of blackness, but they hoped to get something more. And what they did is they got the faintest objects in the universe, which are the furthest away. Furthest away means earliest in time. So in this picture, the things that are big are close by and recent. So this you can see is a galaxy. It's clear that this is a spiral galaxy. And over here, you can see this is a spiral galaxy. And this is a spiral galaxy. And so is this. And so is this. So in this picture, you can see some really close by things. They're not 13 billion years old. They're maybe 2-3 billion years old. What about the smaller stuff? What about the snow on the screen? Well, if you look carefully, you can see more spiral galaxies. They're smaller. If you look even more carefully, you see things that don't have much of a shape to them, and they're smaller. And if you count this, the number of spots on this photograph, there's 10,000 of them. And the smallest ones represent the things furthest back in time. Yes?
Maybe it's wrong, but it seems to me there's a predilection of the universe to do spirals.
The universe, no, the only reason the universe is not predisposed to do spirals. The universe also likes to do ellipticals. It also likes to do lenticular. It also likes to do irregular. So the spirals are the ones that you catch your eye the most.
What's lenticular?
Lenticular means
Like a
lens, flat like a lens, with a bulge in the center, perhaps, but having no real structure. And I have thousands of pictures of these to show you, because that's one of the things I'm going to do here. I'm going to sit here and go next, 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 and oh look, there's that. Oh, there's that. You know, but so half of you will fall asleep. I'm scared to do that, but it's so beautiful because the universe is so beautiful. What we're doing is we're flying. It's like we're taking, in this course right now, we are taking a jet plane and we are flying over all that is interesting. It's like you're going all the way to India and you're skipping over all of Europe, all of Asia. You're on the way to India. You're looking down, you see nothing. We're skipping all the stuff that's interesting on the way to India. Except unlike traveling to India, when we finally get to our destination, it'll be remarkably like the place we left. Because the universe is more or less the same everywhere, which is not the same thing as the Earth. The Earth is not the more or less the same everywhere. It's different everywhere you go. So what we're doing is we're going back in time, which makes it interesting. So what we can do is we can go back in time and we can fly through this. We can fly through this picture. The reason we can fly through this picture is we know, and it's really amazing, we know for each one of these little dots, we know how far away they are. And we know that because I skipped something in this class in which I would have explained in this lecture that I intended to begin with the cosmic distance ladder, which could explain how I know how far away all those things are. I'm skipping that for right now. And I'm just going to tell you we know how far away each one of those things are. So I can assign a distance to each one of those little dots.
Depending on its size also. Right?
Well, if I know this distance, and I know its brightness at a particular distance, that I can know that as I imagine getting closer to it, it should get brighter as I get closer to it. So if I'm creating a movie, what it's like to travel through this soda straw on the way to those distant galaxies, I should be able to see them get bigger as I get closer to them.
Yeah.
Yes.
You have indicated in the past weeks how far how well you know how far they are. You know there's a formula and so
Yes.
forth. But 10,000 in that picture, no. It doesn't.
Yeah.
Sorry, but have you counted them? It just doesn't seem like.
Have I counted them?
In this picture.
The people who spent millions of dollars to do that did, I can tell you.
And they say this guy,
Yeah.
this frame has 10,000?
Yeah. Mm-hmm.
Okay.
Yeah. Mm-hmm. Yep.
So there's a lot that are tiny teeny.
Yeah. Yeah, it says it right here. If you need, I copied these words, 10,000 galaxies. I copied those words. Okay, so I have to trust that. Okay, but you don't have to trust it. You can look it up.
Or count it.
Right, or count it.
Can you? Sure, I have nothing to do next week.
So this, they made a movie of that, and hold on. So this is that same picture, but now they're taking us on a journey through the Hubble Deep Field. Okay, so you can see the galaxies swinging by us as we go, and I assume they're making the images larger as we go further and further down. But notice that the galaxies are small, even though they're making them bigger as we get closer to them. The galaxies are small because when the universe first began, there was a lot of fluff, and the fluff came together to make bigger galaxies. But in the past, they were little itty-bitty galaxies, and they became the big galaxies that we see today. Yes. So we just flew through 13, maybe 30 billion light years. We just did that. Did you enjoy the trip?
Ooh,
Okay.
I feel nauseous.
Yes. Right. 30 billion light years. Right.
And they were also irregular. The shapes were irregular.
Irregular.
Like glass on a beach before it gets hit by thousands of
Right.
years of water washing and then smoothing out the edges.
Right. So these galaxies are irregular. What takes to get to regularize.
Regularized.
There you go. Not going to try to say it. Is time and the fact that they all get together. Imagine you take a 1,000 little galaxies and you put them together under their own influence. They will form into a spiral shape more likely than just one, which doesn't have enough gravity. It's just barely holding on. If you take 1,000 of those galaxies, they will have an enormous influence on each of them. And so you get the structure as you put more together. In the past, you had less structure. In the present, you have more structure. So you took a tour. You took a tour of the universe. You went to the end of the universe, and you did it in a very short amount of time. I have the universe right here, and so I can just, it's no problem for me to take apart the universe. Unfortunately, untangling a piece of rope is harder. Okay.
That's string theory.
No, this is Laird theory. This is Laird theory. Okay, this is Laird theory. So what Laird did is he took some rope and I marked off gradations every foot or so. Okay, every foot. There's a gradation. Okay, so I got it in my head that this was the distance between the Earth and the Moon. And this is 10 times further away. So this is not 250,000 miles. It's 2.5 million miles, which doesn't make it quite to Mars. And then this is 25 million miles, and that's probably around the distance to Mars. So look, this is to the Moon, then 10 times bigger, then 10 times bigger. We're at Mars. We're at Mars, okay? You see, but this is wrong because the first piece is to the Moon, and then 3 pieces later I'm at Mars. Well, that's wrong, but that's what we're doing in these pictures. What we're doing is each piece is 10 times bigger than the last piece, which is why you were able to get to the end of the universe so quickly, because it was only a matter of going to the end of this piece of rope, and you got to the end of the universe. There are 16 of these segments here. 16. I made a mistake. There should be 17. There's only 16 segments.
What do you mean made a mistake?
Well, when I made this up, I made this thing up and I just started painting the segments, and I did the math wrong. I wanted to start out at the Earth Moon and come to the end of the universe. So I wanted this to be 250,000 miles, and by the time I got to the end of the rope, I wanted it to be 45 billion light years, so that would be the radius of the known universe. but I didn't. I was missing a segment. So it's only 16. So I only got to 4.5 billion light years. And there's an entire segment that's missing that would go the extra 10 times, not 4.5, but 45. I, by accident, left out 99% of the universe when I did this. If I had only added one more segment, I would have done 100% of the observable universe. So at no point in any of these pictures can you ever imagine that I'm doing all 17 segments. We're only seeing a piece. Maybe you were seeing this segment of the universe in any of these pictures. Maybe you were seeing this segment of the universe in any of these pictures, because I'm going to show you some more pictures. And the question is, how far out are we looking, Laird? You know, how big a picture is it that I'm showing you? Well, the picture that I showed you earlier on the screen, yeah, this one. So this one now is 125 million light years. Let's call it 500 million light years. 500 million light years is nothing like 90 billion light years. So this looks like the universe, but it's really just a teeny itty bitty piece of the universe. Yet I say this is like, because the universe looks like this everywhere you look. So Barbara, who isn't here, Barbara is coming at this very moment. Barbara, I'm talking to you. Barbara asked the question, is the universe the same everywhere? Okay, well, this is a small piece of the universe. And is it the same everywhere? And so what do you think? I would venture to say that the universe at this scale is the same everywhere. You might say, well, you know, because there's a void there, you see, and there's a void there. I'm going to try this with the cursor. There's a void there, and there's a void there, and there's a void there. This is the biggest void I see, but there are a lot of voids of more or less the same size all over the place. So I think this is a fair representation of what I would call the universe is the same everywhere. Yes?
The string that you showed us, that string, would that be factorial advancement?
Not factorial. The word that you want is exponential.
Exponential, but factorial also has it.
Factorial is a good word.
Yes.
Save it for another time. Okay? Really, has nothing to do with this. Really. You want to know what factorial is?
I know it's not what.
Well, factorial, okay. 4 factorial is 4 times 3 times 2 times 1.
Yeah.
5 factorial is 5 times 4 times 3 times. The universe is not made up of factorials anything.
That is the word that's a much better word, yeah.
It's exponential. Or if you like, logarithmic, which is the inverse of the word exponential. Because this is logarithmic, this is log 1, this is log 2, this is log 3, this is log 4, the way up to log 16, but it also means 10 to the 16th. Okay? 10 to the 1, 10 to the 2, 10 to the 3. Hold on one second.
If what you say is so, how
Of
would
course.
scientists focus on a part of the universe which is black, inky black, and leave the camera on for 2 weeks and still not find stars and still find, you know, I can't imagine why there would be this emptiness in a certain part where it's inky and blah, 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 where it's not a redundancy of what's going on everywhere.
They just said, where can I point a telescope where there's no stars?
Right, but why wouldn't there be stars everywhere?
Well, first of all, you pointed out of the plane of the Milky Way, because the Milky Way has stars that direction, so you should look this way. Okay? So there's less stars there. And then you find a spot that has no stars. There's fewer and fewer until you find a spot that has no stars. That's where you point the telescope. It's a good place to do it. So let me show you other versions of the universe. And what I mean by other versions of the universe, what I mean is other versions of the large-scale structure of the universe. So this is a simulation of the universe forming. It's about 1 billion light years on one side, and this simulation takes 11 seconds. So I will, by needs, need to repeat it. This is the universe over 13 billion years, and it just ended. I'll play it again.
Sound.
No sound. There's no sound on this.
No, I said sound. Play it again, sound.
Yeah. So this is how the universe forms. It comes together, produces these voids. There you go again. This is, I'm going to play this type of movie again, but it's going to take not 11 seconds, but take closer to 5 minutes to play. This was done 10 years ago. Computers are faster and bigger now, and they can do more things. So, we can look at other simulations.
This computer simulation starts just 12 million years after time zero and evolves within a volume 350 million light years across.
That's small. 350 million light years across. Multiply that by 100, and you get what the size of the universe is. So this is still an itty-bitty part of the universe. 350 million light years, like the kind of picture I showed you at the beginning. That scale.
Not everything is known, including the nature of the dominant substance known as dark matter. On the left, you can see how gravity draws dark matter into filaments, like a spider's web. On the right, gas heats up as it falls into a series of deepening gravitational wells carved out by dark matter. Within the volume, tens of thousands of galaxies take shape, mainly within the filaments of dark matter. Where these filaments meet, something strange begins to happen that will affect the character of nearly every galaxy or star. Vast bubbles of hot gas begin to form and expand outward. On the left is a closer view of galaxies that are falling into one of the central regions. On the right is the gas that envelops these galaxies. As gravity draws these galaxies together, waves of hot gas explode outward. This happens when giant black holes in their centers blast inflowing matter out in ferocious winds and jets. In time, these hot bubbles push out well beyond the central galaxies. This has the effect of limiting the amount of gas that can fall into central regions, allowing smaller galaxies to form on the periphery. It also seeds the wider universe with heavier elements created in early generations of large stars. Those elements you and I are made of. This is the story of our galaxy and our world. The coming together of dark and ordinary matter. That heat up as gravity compresses them. That leads to the production of metals and stars that are spread throughout the cosmos. Finally, there is light, given off by ordinary matter in a variety of wavelengths that we can record from our tiny outpost. In a galaxy, and a universe that is dynamic and complex on all scales of space and time.
So why did I show you that? I didn't show it to you so you could really become knowledgeable about how galaxies are formed. That wasn't my point. My point was something much simpler. Gee whiz, look at all those galaxies. And gee whiz, there's an awful lot of them. And gee whiz, they seem to form some sort of structure in the universe. So the universe is has a structure to it. It has the voids. It has the filaments. It has those central clusters. I wanted you to know that what you were seeing were thousands of galaxies. Galaxies, some of which are as large as the Milky Way. If I'm trying to tell you how big the universe is, which is, if you will, the ongoing theme here, not so much, gee, how did galaxies form? That it will hardly be the conversation in this room, because that's a harder conversation. I want you to just get, ooh, there's a lot of them. I can't imagine how many there are, but there's more than I can imagine is a good start. And the another picture I want to show you would be how our own galaxy started, however. And that one is, if you will, a giant cosmic simulation. So this one would be the growth of our own galaxy, if I can find it. Yes?
In the narration, it indicated that the dark matter was pushing the strands, the filaments, toward the formation. And that meant to me that the dark matter has mass and density. And that seemed surprising to me for some reason, because the dark matter we've been playing around with didn't seem to have that kind of urgency or that kind of physical excitement.
So dark matter is matter. If we did the same simulation and we removed dark matter from the simulation, because dark matter is dark because we've never seen any of it, okay, at all. We see signs of it. We need to postulate its existence. We see its influence, but we don't have a bucket of it, not even a single molecule particle of it. So when we play with dark matter, and if we remove the dark matter as if it's not real, the simulation that I just showed you wouldn't work. It wouldn't simulate anything that looks like our universe. You have to throw the dark matter back into the equations that were cooking inside the computer to get something that looked like that in the first place. I don't know if that answered your question. Yes?
everything that is today was created in that first instant, meaning you have said
did the Big Bang create everything that is? The answer is yes.
So, following that, you have said that everything that we are, all of the elements, come after, I always thought, after stars have exploded.
Yes.
And things change.
Right.
And form different things. So
the elements that we're made of did not form in the Big Bang. They formed inside of stars subsequent to the Big Bang, yes.
Later, so everything that we are is not from the beginning.
Right, but the matter inside of us, which has been altered to be fused into carbon and oxygen, was fused from hydrogen that existed at the moment of the Big Bang. So our carbon atoms have a history of having been hydrogen atoms once. But that was formed in the Big Bang. So if you like, our protons were formed at the Big Bang. Okay, and
so it became more complex.
Right.
There was a possibility from the beginning, but it
we were possibilities at the beginning. Yes, yes. I want to show you. Okay, so what we're going to do is we'll pick up on this. The idea is I'm going to show you again how we get to some of this stuff, and eventually we are going to, having climbed the cosmic distance ladder, we're going to in fact go see what we missed. Like everything in the universe, there's some very pretty pictures of the universe that we haven't seen any of because we were flying over it in our jet plane. Now we're going to land in a few places to see what it's like.
Do you think that all these things that coalesced were meant to do that, or was it just a
We're meant to?
crapshoot? I know you don't mean that, but I mean all these elements.
No. I mean, I know you don't believe in God, so that's not what you're saying.
No, but I mean,
But the laws of the universe
yes.
Are such that they're designed by the almighty non-creator to give us us. Without those laws, we wouldn't be here. But in the other multiverses that you like to visit in your brain, those universes don't have our physical laws, and so people like us cannot exist in those multiverses. We're in the lucky one.